So this demo is going to show how we can generate a plane using triangles. As you can also see here, we've got UVs mapped. I'm using basically the red and the green channel to map them, and I can demonstrate this in wireframe as well, so you can see how the triangle strip is sort of generated there. So this is the OpenGL version. If we have a look, it's similar setup as before. So OpenGL window, the initialization, we've got our look at matrix to give us a sort of a camera. We've enabled depth testing multi-sample. We've got a line shader here. This is different from last time. What you'll see now is I've got 3 inputs. So I'm inputting a position, a normal, which in this demo is unused, but later on we're going to use the same sort of data layout with normals in to do some shaded rendering, so it's in here now anyway, and UVs. And what gets passed out of this shader, again that's superfluous at the moment, is the UV that's being passed out, which I'm going to use in visualizing the color, and the output position here from the model view projector uniform. And then in the element where I'm shading, all I'm doing is I'm setting red and green of the output color to be the current UV. So you can then see when we run this, again it needs a quick resize because of the mapping issue. So you can see now the UVs run across from red to green, and then you can see the blends as it goes across the different levels there. So quite a useful way of visualizing UVs when you're trying to debug things going wrong as well. So the key part of this one is the create triangle plane. What I've done here is I've generated a NumPy data type. Now this is really useful. So you can specify individual named and sized types. In this case the ones are superfluous. You can just say X is an MP float 32 and it will be an individual 32, but it is quite useful to sort of do that in there because other times we may be having bigger data types and things like that. So in this case what this is generating is an array that has the structure X, Y, Z, normal X, Y, Z, so in X, N, Y, and Z, and U and V. And what we can do is we can access these as named types within a NumPy array as we go through. So in this case I'm creating an empty array which I've called vert. It is being constructed with a 0, 0, 0 for the X, Y, and Z components here. It's going to have a default value of the normal, so normal X, Y, and Z. Effectively in this case I'm going to have the normal pointing upwards, and every single entry is going to have a normal pointing upwards, and a UV of 0, 0. And obviously this is the data type that it's doing it. So what I've done is created an empty array. I'm now going to go through and process and set each one of the vertex types here. So as we go through, I've pre-calculated some elements here. So what I've got here is I've got the width over 2, depth over 2. I've got my UV values. I've got DU, DV. So this is my step in U and V. And then I've got steps within the individual elements as I go through. And then I'm going to generate my counterclockwise triangle, my clockwise triangle. I'm going to populate the vertex data structures there, increment my index and go into the next one. I just realized here actually that this empty data here is actually no longer used because I'd renamed it to that one there. Just validate that that's there. No, it didn't. So where is vert being used there? Oh, vertex data and vert. Right, so yeah, no, vert is my empty one that I've created there. Sorry, I'm getting confused there. So I've created an empty vert one and then I'm appending it to vertex data. I got it the wrong way around. So this is a single element, and then this is my empty array of width by depth by 6, which is basically the 6 are 1, 2, 3 for one triangle, 1, 2, 3 for another triangle, and then that gets populated into this vertex data at the array each time. Sorry, I should have looked at my code before I started talking about it. And then I'm basically just populating the triangle elements, as you can see here. So 1, 2, 3, like that. Now, unlike web GPUs, we'll see later, we can sort of get away with the winding easier in OpenGL, but basically what you can see here is we are going in that direction as we're going through there. So we are going around counterclockwise. And again here, 1, 2, 3. So again, counterclockwise as we go through to specify our two triangle elements there. Although that's drawn the wrong way around to that one as well. ASCII art's not my strong point. Now the data has been generated. We have our vertex attribute array generated here. We create our binding, so make that currently active so everything gets populated in there, and then we generate a single buffer in this case, and what I'm doing is I'm populating this buffer with the entirety of that data. And then what I've got to do, so I've got a single data now with basically spanned elements within that data. So what we need to do next after this, so this copies it across, is to tell it how big and how it's offset into the array. So input 0 of our shader has 3 components, type float, no need to normalize them. To get to the next one, you need to move this many bytes. So vert.n bytes is the size, basically, it's the equivalent of calling size of this array in C, so size of this structure. So n bytes is from numpy, and it just gives us in bytes the size of it. So this tells us each time how to get to the next entry. Now this one tells us how to offset into that data structure to grab the elements. So this first bit, we've got our structure up here. It's at 0 because we don't need to go any further. Now if we want to get to our normal, we need to skip 1, 2, 3 components. But remember, each of these components is a float 32. A float 32 on most systems is 4 bytes. So therefore, we need to move 4 bytes times 3. And to do that, we can, here we go, say 3 times float size, so 3 times 4, which will give us 12 to offset into it. And then again, same here, 6 times 4 is giving us the offset into the array each time. So these calculations do get a little bit complicated after a while, a bit annoying, but it's quite useful when we have our data structured in this way that we can use the built-in elements here. We can calculate float size quite easily by using C-type size of. That should make it portable and cross-platform. Not that we really need it for the Python side of things. Now this is ready, again, drawing is quite easily. We enable the VAO, we make a call to draw arrays, it will draw our grid, and it's nice and easy. We're enabling wireframe mode by just enabling the GL polygon mode. This changes how rasterization is done in the back end of OpenGL. As we'll see when we get to using this in WebGPU, we can't do that easily. We have to use other methods of doing it by using shaders and other things. So that's the simple demo for the triangle grid. What we'll do next is we'll look at the WebGPU versions of it.